everyone, my name is Shilpa and today I am presenting the paper A Survey of Graph Transformers, Architecture, Theories and Applications. This is a 2025 AIRX-IV survey that explores how transformer-based architectures are adapted to work on graph structured data. Okay, so what's the motivation behind this? Graphs are everywhere in real world systems. We use graphs to represent social networks, molecules in drug discovery, knowledge graphs in NLP, and even road networks for traffic prediction. Because graphs encode relationship between entities, we need models that can reason not just about individual nodes but also about their connections and global structure. Okay, what is graph transformer? A graph transformer tries to bring the strengths of transformers, especially self attention, into this graph learning. We treat nodes and sometimes edges or subgraphs as tokens just like words in a sentence. Self attention allows each node to attend to many other nodes, potentially across the entire graph, which helps captures long-range dependencies. To respect the graph structure, graph transformers inject additional information such as graph distances or positional encodings directly into the attention mechanism. So next is what is the architecture taxonomy. The survey proposes a taxonomy of graph transformer architectures. Broadly, it categorizes them into structure enhanced transformers, which modify the standard transformer to be graph aware. Then comes GNN transformer hybrids, which combine GNN layer and attention layers, and hierarchical or subgraph based models, which work at multiple scales to handle large graphs. This taxonomy helps us understand the design space and compare different approaches. So, firstly, let's take structure enhanced transformers. This this starts from a vanilla transformer architecture and then inject graph information. A common technique is added to distance aware biases and to the attention score, so the nodes that are closer in the graph get different treatment than distance ones. And another important idea is a graphical positional encodings using tools like Laplacian eigenvectors and using tools like and also other tools like random walk features to encode where a node sits in the graph. These models are appealing because they are straightforward extensions of existing transformers. Let's take the next one, GNN transformer hybrids. In hybrid architectures, we explicitly combine GNN layers with transformer layers. GNN layers focuses on local neighborhood aggregation information from immediate neighbors. Transformation layers then provide global attention, letting nodes attend beyond their local neighborhood. This combination often yields a good balance. We preserve the inductive bias of GNN while gaining the global expressive power of transformers. Let's consider the last one, hierarchical and subgraph models. Here, when graph gets large, applying full self attention to every pair of nodes becomes too expensive. So hierarchical and subgraph based graph transformers addresses this by breaking the graph into clusters or subgraphs. The model can apply attention within subgraphs and then at a higher level across subgraphs. This multi-scale approach improves scalability and captures structures at different resolutions from local motifs to global communities. Okay, let's consider theoretical insights. The survey also reviews theoretical works related to graph transformers. One key question is expressivity. Can this model distinguish between more complex graph patterns than standard GNNs? With appropriate structural encodings, the answer is often yes. Graph transformers can be strictly more expressive. Another area is generalization. When do these models perform well on unseen graphs or distributions? Finally, there is the complexity aspect. Attention has quadratic cost in the number of nodes, which drives research into efficient and sparse attention mechanism. Okay, let's see what are the applications of this. Graph transformers have been successfully applied in many domains. In molecular modeling, they help predict properties and designs new molecules by capturing long range interaction between atoms. In recommender systems, graphs represent user item interactions and knowledge graphs, and graph transformers are used to model complex multi-hop relationship. In knowledge graphs, they improve link prediction and reasoning over relational structures. They are also used in traffic networks and social network for tasks like forecasting and community detection. So, if there exists application, there should also be limitations to it. So, what are the limitations of this? Traditional message passing graphic neural network have been very successful, but they come with limitation. First, if we stack too many GNN layers, we run into over smoothing, where node embeddings become almost indistinguishable. Second, GNNs can suffer from oversquashing, where information from far away nodes gets compressed through a narrow neighborhood. And overall, they struggle to capture truly global patterns in large graphs. These issues motivate the development of graph transformers. Okay, now we know the limitations, and the next thing is what are the challenges and where in future the direction is, like in the future directions. Despite the promise, graph transformers still face several challenges. First is scalability, making attention work efficiently on very large and dynamic graph is an open problem. Second, interoperability. While attention gives some insight, fully understanding why a model made a particular decision on a complex graph is still very difficult. Third one is the community needs a better benchmark and evaluation protocols to fairly compare models. And finally, robustness to noise, missing edges, and distribution shifts remain an important research direction. I would like to comprehend the whole thing. The summary of this whole paper is graph transformers combine the structural bias of graphs with the global reasoning power of transformers. The survey I presented organizes this field into a clear architectural families, reviews theoretical results, and highlights a wide range of application. As graph data continues to grow in importance, graph transformers are likely to become a core technique for building more expressive and flexible graph learning systems. Thank you for listening. I'm happy to take any question. Thank you.